I'm not at we'll see how it goes. Gotta get through,
Good afternoon. Yeah.
Are we gonna do a conversation?
We're scheduled to, but sometimes we don't have time, so we'll have to see. Yeah.
That's good, because that's like, I feel like that's like the hardest.
Yeah, well, one of them for sure. Yeah. How are y'all?
Here?
Yeah. It's good to see you. Thanks for being here. Do y'all have any homework questions? So we've completed 2-1, 2-2, 2-3, and 2-4. So we're going to start 2-5 then if there aren't any questions. 2.5. We did sort of allude to 2.5 as well. We kind of looked, before we started 2.4, we looked at the gist of 2.4 and 2.5, but here's again a reminder, 2.5 limits at infinity, where 2.4 were infinite limits. Okay, so 2.4 we looked at vertical asymptotes with limits, and 2.5 we're looking at limits at infinity. So this time x is approaching infinity or negative infinity. So these limits at infinity, determine end behavior. So that's for any function we look at. Doesn't have to be a polynomial or rational square root. It can be trig functions, it can be any kind of function. When we compute a limit at infinity, what we're determining is the end behavior of that function. In other words, on the very far left and right of the graph, what does the function look like? What is it doing? Okay. So some applications of limits at infinity are the spread of the disease, population increase, does the population level out, that kind of stuff. Okay. So this is just a diagram illustrating that idea. This is an actual function that you have seen before, and we'll sort of address when functions have horizontal asymptotes, when they don't, as we go through. But the idea is, as x approaches infinity, does the function approach a specific limit? As x approaches negative infinity, do we have a different limit in that direction? In either case, if x is approaching infinity or negative infinity and your function approaches a finite number, that will correspond to a horizontal asymptote. So does everyone see the sort of the contrary aspect of what we've looked at compared to what we're looking at? Right. In 2.4, what we said was, here in 2.4, if we compute the limit as x approaches a finite number on whatever function, and we're given, or we're able to determine that it's positive or negative infinity, then this tells us that we have a vertical asymptote at A. And of course we looked at two-sided limits here. But in 2.5, we're computing the limit as x approaches infinity or negative infinity on a function. And if it comes out to be a finite number, we'll call it L, then we have a horizontal asymptote at y equals to L. Okay, so hopefully intuitively that makes sense as we progress this way or this way, and the function flattens out towards a specific value. That's a horizontal asymptote. And so that's our definition of a horizontal asymptote. So it says if the limit as x approaches infinity on the function is equal to a finite number L, then we've got a horizontal asymptote at L, which is what we just wrote down. So does that all make sense? Does anyone have any questions or comments about that? So I think it's a very logical way to define a horizontal asymptote. If you were trying to define to someone what a horizontal asymptote is, you could explain in words what it is, right? As far as like an algebraic interpretation, we said, all right, well, here's this rational function, where's the horizontal asymptote? You had to look at the degree of the numerator versus the degree of the denominator, and based on comparing those two degrees, you had like 3 outcomes. So it was like, if the degree of the numerator is greater than the degree of the denominator, then this specific thing happens. If something else, then this happens, right? So you could explain it in those sort of terms, but it, you know, probably when you were in algebra, it wasn't totally clear, well, why does that work? Why if the degree of the numerator is larger than the denominator, why is there no horizontal asymptote? So this definition using limits hopefully makes sense of all of that. Okay, so we sort of have a reverse role here, and I need to make this a little more precise. But if we have a quotient, and the denominator of the quotient is getting larger and larger, here we probably need to say something to the effect that A is finite. Yeah, we'll just say that here. But it's sort of the reverse as to what we were looking at in 2.4. In 2.4, the denominator got smaller and smaller, while the numerator was fixed. So we said, well, what happens to the quotient as the denominator gets smaller and smaller? The quotient gets... Somebody has it, I know it.
Can you repeat that one more
If
time?
the numerator is fixed, like say the numerator is 5, but the denominator is getting smaller and smaller, what happens to the quotient? It gets bigger and bigger, right? That's why we had these kinds of things coming out when we evaluated the limit. So kind of take that and reverse it. If you've got a fixed number on top, but the denominator is getting larger and larger, what happens to the quotient? It gets smaller and smaller. So that's kind of what we're dealing with here in some instances. Okay. Any other questions, comments? Okay, so we'll see this definition in a moment, but is it possible to calculate a limit at infinity and get infinity as a result? Can that happen? Somebody's shaking their head, yes. So what are you thinking of? What kind of function are you thinking of? Like, what are you picturing?
I was thinking like x squared.
Like x squared, right? The function x squared. No matter how far I go out in this direction, the function still is growing arbitrarily large. And no matter how far I go out in this direction, the function is arbitrarily large. So yeah, for sure, we've seen those types. What kind of functions do we call those? A quadratic is what type of function? A what? A polynomial, yeah. So we see this, I guess, in some other instances, but specifically for polynomial functions, this always happens. So if f of x is a polynomial. So what am I actually doing here? We said on the very first page, if I compute the limit at infinity on any function, what does that tell me about the function? What is this specific term we're using here? Limits at infinity determine
Horizontal asymptotes.
horizontal asymptotes in some cases. More generally, though, some functions like the in behavior. Some functions like polynomials, they don't have in behavior. As we go off this way or this way, the function doesn't die off or flatten out, right? But it does describe the behavior at the end, regardless of how you want to look at it. Regardless of whether a function has a horizontal asymptote or not, we're still computing limits at infinity, and that's going to always describe how the function behaves at its end, regardless of whether a horizontal asymptote exists or not. So what we're saying here is we're calculating the limit at infinity on this function, and in general, that's telling us what is the end behavior of that function. So here, since we've specifically named polynomial functions, and I guess a question would be how, before limits, before we even, looked at this definition at limits at infinity, how do we determine in behavior of polynomial functions? We're just going to try to tie whatever we can tie to prior knowledge. We're going to try and do that. Yeah.
The exponents or to the powers that, if it's even or odd, can determine the end behavior.
Okay,
of it.
right. So we'll make that a little bit more precise. But the exponents, remember the exponents determine whether it's doing this or this or this, right? What else affected the arrows, where the arrows went?
If it was negative or not?
Right, if it was negative or not, yeah. So there's specifically, we're looking at an exponent and a coefficient, right? The number attached to like an x squared. But it had to be a very particular thing, right? Like if I said, what's the end behavior of this function? We can't just look at one of those. We had to look at a very specific one. Which one do we have to look at to determine where the arrows go?
The leading coefficient.
The leading term, yeah. We had to look at the leading term, and how did we find the leading term? We simply looked for x that had the highest power on it. We said, all right, that's my leading term. Here's the degree of that polynomial is 6, and here's the leading coefficient, right? So when we looked at the leading term to determine where the arrows went, we called that the leading term test. Does that ring a bell? The leading term test? So that's how we determined end behavior for polynomials before limits came about. Leading term test. And so, we'll see exactly why it's valid, why we could have done that in algebra and it was accurate. But let's just list out the leading term test. So we've mentioned that there's two things needed. You need the degree and you need the sign of the leading coefficient. So if you'll remember, like the generic definition of a polynomial would be like a sub n, where that's just some number, and then we have x to a power, and then we decrease the powers by, whatever, 1. And, that a sub 0 is a constant. Right? So that was the generic definition of a polynomial. So what we say by leading term, we just mean this thing right here. It's got the highest degree, and that's how we know what the leading term is. Okay. So there was two conditions. We had an even degree function, even degree, and an odd degree. In addition to the highest power on x, we also had the coefficient attached to x. So again, that leading coefficient we're just going to denote a sub n. So if our leading coefficient could have been positive or negative. And then we had only 4 outcomes, 4 polynomials. Just be mindful that we are just talking about polynomials right now. So an even degree with a positive coefficient, that was like a positive x squared. The arrows are both pointing up. You know, and sometimes you had the squiggles in the middle. If we had an even degree but a negative coefficient, what happened? They point down, right? Because the negative times that number just reflects it across the x-axis. Okay. Squiggles there. Sorry, this board is awful. Okay, pointed down. Odd degree with a positive coefficient. Started down and then ended up. Yeah, so started down here. Ends up here. Again, negative coefficient, it just reflected that thing across the x-axis. So it starts up and ends down. Okay, so quick algebra review there. Does anyone have any questions on that? So then let's look at, for example, we've got this function we'll call f of x, defined as negative 3x to the fifth, plus 10x to the fourth, minus x to the third, plus x minus 4. So then a question that you've seen previous was, what is the end behavior? What is the end behavior? Usually you just drew it. Yeah. So what is the end behavior of that particular polynomial? Starting up and then ending down. Do you all agree? Like this. Yeah, so again, we're just looking at, here's our leading term, odd degree, negative coefficient. And then that was part of your graphing process. The other part of your graphing process was to figure out what these squiggles were actually doing. So then you said, all right, well, let me factor this thing using synthetic division. And then based off of how many times the factor occurred, I knew whether or not we crossed at the 0 or bounced off at the 0. So hopefully that's sort of vaguely familiar. But, you know, now what we want to do is we want to look at it this way. Whenever you see the phrase, what is the end behavior, you want to think about computing a limit at infinity and a negative infinity. So what's the limit on this function as x approaches infinity, and what's the limit on this function as x approaches negative infinity? So that's how we want to start thinking of end behavior. But, you know, from this end behavior or the leading term test, maybe we should ask how or why. Why does this work, or how does this work? And we'll remind ourselves here again that when it says end behavior, what that means is calculate this limit, or this limit, and this limit. On whatever function you're given, so just denote that f of x. So we know when we see like a polynomial, what's the end behavior? Hey, let me just look at the degree and the leading coefficient. We're basically asking now, like, how does that work, or why does it work? Why are we able just to look at that leading term? So maybe just to give you a hint, is if x is getting larger in either direction, go back up to this specific example. X is getting larger in both directions to answer the question about end behavior. So how come we're just able to look at the negative 3x to the fifth, for example?
Because infinity to the fifth is a lot bigger than infinity to the fourth or infinity to the third. So
Right.
you kind of assume that that's going to be carrying the whole function.
Exactly. Yeah, so in the sense that x is getting larger and larger, what we're looking at is a really large number to the fifth is much larger than the same really large number to the fourth and to the third and to the first, right? So it's like, it's an order of magnitude larger. X to the fifth is a power larger than x to the fourth, which is 2 powers larger than x cubed. So if I said, just for instance, take 1,000 and raise it to the fifth power, and then add 10 times 1,000 to the fourth power, you can do that on your calculator, but you're pretty much still going to have 1,000 to the fifth power, right? So if you don't believe me, just type in a really large number for x in one of those types of functions, and see that it's always a lot more closer to the highest power than it is to the lesser powers. And the reason, again, that happens is because in behavior is saying let x go to infinity. And so as we allow x to go to infinity, the lesser terms of the polynomial don't matter. They don't really affect the function. So as x approaches infinity in either direction, the lesser terms, we'll just say, it's not technical, but we'll just say do not matter. So this is like a really important idea that it's only in the context if x is getting larger and larger that the lesser terms don't matter, right? You certainly wouldn't say, if somebody told you to evaluate that function at 0, you certainly wouldn't just use negative 3 times 0 to the fifth and say you're done, right? So in any other context, those terms, all of those terms matter. It's only in the context that x approaches infinity or negative infinity that they don't matter. So only in that context. All right, and so basically, does anyone have any questions on what we've done, or comments or anything? So basically what it's telling us, all of this stuff, we can just briefly summarize. And say to compute a limit at infinity, and again, we'll remind ourselves, limit at infinity, that's in behavior. To compute a limit at infinity or to determine the end behavior on a polynomial function, we need only to work with the leading term. Just as we did in algebra, we're just making this explicit. To compute a limit at infinity on polynomials, here's what we need to do. So for example, what is the limit as x approaches infinity, and we'll use that function we had above, the negative 3x to the fifth. I forget what else was there. 10x to the fourth, x cubed. Was it minus x cubed? Plus x minus 4, I think. So you should get it in your mind at this point that whenever you see this, we could also reword this limit question just how we worded it before. I could take that limit as x approaches infinity out and say, what is the end behavior of this function right here? So they're the same exact question. So here's where this concept is like really important, because if you just try to plug infinity in for all of this stuff, it's going to be super misleading, because this is going to be negative infinity, this is going to be positive infinity, negative infinity, positive infinity, and negative 4, right? So if remember, as a symbol, infinity is not the same, this infinity is not the same as that infinity. It didn't come from the exact same term, so it's not the same infinity. But if you're looking at it from a purely symbolic standpoint, you'd say, you might be inclined to say, well, negative infinity plus infinity, that's 0. Negative infinity plus another infinity, that's 0. So my limit at infinity is negative 4, right? No, totally not right. What we have to remember is the same procedure we just talked about, the same procedure we remember from algebra when it asks you to determine the end behavior of a polynomial. You just look at the leading term. So computing the limit at infinity on this function is equivalent to computing the limit at infinity on its leading term. Because remember, the infinity to the fifth is getting larger much, much, much more rapidly than any of those other infinities. Is everyone okay with this? You're just gonna have to remember that. That's what you've done in algebra, and that's what you did in pre-calc, but now we're just making it specific with this limit notation. And then once we've isolated that leading term, at that point, then if it's still, it's hard to determine or whatever, we can look at this more symbolically, if you will. So it's like we've got a negative 3 times a arbitrarily large number to the fifth power, which is of course negative 3 times an arbitrarily large number. So negative times a large number is a negative large number. Okay, so we'll remember this one here. Let's call this 1, and we'll also compute the other end. So typically when people are asked to compute the end behavior of something, they'll only compute the limit at infinity and forget the other limit at negative infinity. But to be a true end behavior, you've got to know what's happening on both ends, so positive and negative. So that's what we'll compute. What's the limit as x approaches negative infinity? I'll just write all of this out for this particular function. Same question, what's the end behavior? But this time, what's the end behavior on the far left of this function here? Well, that's equivalent to the limit at negative infinity on negative 3x to the fifth. The leading term again. Now we have x approaching a negative infinity. So we've got negative 3 times a arbitrarily large negative number to the fifth power. So when we raise an arbitrarily large negative number to the fifth power, what do we get?
It's still negative.
It's still negative, right? So we have the negative 3 times that negative infinity, which is positive infinity. Again, the smaller terms go away, or the lesser terms in degree go away because we are at infinity. So this is how we want to start to get accustomed to looking at the leading term test or in behavior in general. Because not all functions have leading term tests. And note, our work actually just verifies what we drew out originally, right? As x approaches negative infinity, the function approaches positive infinity. So as x is way out here, the function's way up here. The other one, as x approaches positive infinity, the function approached negative infinity. So as x is way out here, our function is way down here. And that validates the in behavior from the leading term, right? So all of this would be filled in at a later time. But those limits are giving us those two things. Where the arrows go. Does anyone have any questions?
Will we be asked to kind of graph it as well, along with understanding?
We really don't get into a lot of graphing until chapter 4. So probably not. I would say that it's important to know what your work tells you about the graph. Just like in 2.4 or 2.3, when we have a hole, when do we have an asymptote, when do we have in behavior, that kind of thing. It kind of solidifies the work you're doing, I think. But no, I wouldn't require you to graph it. Any other questions? There's a couple more, but again, it's the same idea. And what we're going to do is, after we've sort of addressed like these limits at infinity on polynomials, then we'll look at rational functions. So what happens at limits at infinity when we start dividing polynomials? But again, just a couple more to get the idea. And make sure you're identifying the leading term, because not always is it first. Sometimes they'll write it last or in the middle somewhere. But make sure you identify the leading term when you're computing limits at infinity. Okay. Same thing for this one. Still the same function, same leading term. So what's the limit on that function at infinity as x approaches infinity? Infinity, right? We've got a super large number to the fourth, still a super large number, times a positive 5, still a super large number. And as x approaches negative infinity, what happens? Also positive infinity. Super large number to the fourth, the super large number, times 5. So if you forgot the leading term test, hopefully I think this is a lot less to have to remember, honestly, than the leading term test. You just got to remember one thing: how to compute the limit at infinity. At positive infinity, the function is approaching positive infinity, and at negative infinity, the function is approaching positive infinity. So there again is the in behavior for that function. All right, is everyone okay with this? So again, limits at infinity in general, they determine in behavior. Some functions, like these functions, don't have horizontal asymptotes. When functions do have horizontal asymptotes, your in behavior is the horizontal asymptote, right? Because your function always approaches that and never touches it. Okay, we're going to skip that. It's kind of the same idea. So here's kind of what we were working with, more precise. We were looking at infinite limits at infinity. So x is approaching infinity, and the limit was also infinity. It's just a definition there. And then we get the following theorem based on what we've done already as well. So we've got the lowercase p, if you can see that, is a polynomial. And what we're saying here in number one is that x approaches positive or negative infinity on x to the n. When n is even, it will always be positive infinity. So as x approaches positive or negative infinity on an even function, the answer is always infinity in both directions. The second one is for the odd functions. As x approaches infinity for x to an odd power, it's infinity. But as x approaches negative infinity on an odd power, it's negative infinity. So now the signs of infinity match, if you want to think of it that way. So that's this area here. Number 3 in that theorem is saying kind of what we alluded to earlier. If we've got a fixed number where the denominator is approaching positive or negative infinity, then the quotient approaches 0. Regardless of what that power is, right? In number 3, it doesn't specify. N could be even or odd. And the last one is what we've talked about. The limit at infinity on a polynomial is equivalent to the limit at infinity on the leading term. So it's all of that stuff that we've just talked about is sort of condensed there on that page. So we didn't actually look at an example for number 3, so let's look at it here. So like the limit as x approaches infinity on 10 to the, let's say it's 10 times x to the negative 4. So notice 3, explicitly 3 is the only one that deals with x to negative powers. And those things aren't polynomials, right? Polynomials have to have positive powers. So the way we look at that is, in terms of its positive powers, I guess, if it's helpful, but that's the same thing as 10 over x to the 4th. Numerator is fixed at 10, denominator is getting larger and larger, so the quotient gets smaller and smaller. And if we want to write this out like this, we've got to remember it's not that we're dividing by infinity. You've got to think in terms of limits. Infinity just means that thing's getting larger and larger. So it's kind of like in 2.4 when we wrote positive 0, negative 0. If you want to, instead of infinity, if you want to think about that as a large positive number, that's fine. That's the idea. So for a function like 10x to the negative 4th or 10 over x to the 4th, first of all, the limit at infinity means that on the function 10x to the negative 4th, the limit at infinity means we're finding what? What do limits at infinity always tell us? In behavior. So again, we've got to get in the mindset of seeing if we see limits at infinity, whether it's positive or negative, that we're thinking about those as in behavior. That's the same exact question as asking what is the in behavior. So what is the end behavior of 10x to the negative 4? Is what? 0. Yeah, we were looking at it. As x approaches infinity, 10x to the negative 4 approaches 0.
So that's the horizontal asymptote.
Right, now we have a horizontal asymptote because as x gets larger and larger, the y values actually flatten off to something. So what we're looking at just with this function, I mean, we haven't looked at anything else but the limit at infinity. We're saying so as x approaches infinity, this function is approaching 0. So a little bit more work is needed, but whatever it's doing, we do know that it's getting flat out in this direction, or it could possibly be from here getting flat. We just need some more work to determine like where actually is that function. And maybe you can see already where it's at, but just by looking at it. But basically that's all our work with that particular limit has shown us. So horizontal asymptote in this instant. With polynomials, the reason we didn't have horizontal asymptotes is because the limit didn't evaluate to a finite number. Is everyone clear on that? Are there any questions? Okay. So with all of this in mind, then we can look at how do we compute limits at infinity for rational functions. Again, what we're asking it more or less is, what is the end behavior of this rational function? So if you remember, there's on rational functions specifically. So what were rational functions again? Yeah, it's a polynomial divided by another polynomial. So those things had at most one horizontal asymptote, meaning they either had one horizontal asymptote or they didn't have any horizontal asymptotes. Okay. So with rational functions and rational functions only, the limit at infinity and the limit at negative infinity are the same. There's essentially two ways to evaluate. One's more general. It applies to any function like f of x over g of x. But for rational functions, specifically rational functions, the easiest way to compute the limits at infinity is a combination of what we just talked about with limits at infinity on polynomials and our limit laws. So for example, let's just say find the end behavior of this function, f of x equals to 2x cubed plus 3x squared minus x minus 1 all over x cubed plus 5x minus 12. All right, so we'll try to use these things interchangeably, but when we see this, find the end behavior, what we're looking at is two limits. One at positive infinity, the other at negative infinity. Wait, I have enough room here. So the limit, we'll do one here. The limit as x approaches infinity on our given function. Remember the limit law says, provided the denominator doesn't approach 0, what I can do is look at the limit of the numerator and the limit of the denominator, right? So you don't have to write all this out all of the time, but I'm going to go ahead and do that. The limit of the numerator. Oops. The limit of the entire numerator divided by the limit of the denominator. So now with that limit law, what we're doing is we're saying, hey, it's this thing divided by this thing, but the thing in the numerator and the thing in the denominator are both polynomials, right? So in order to evaluate the limit at infinity on the numerator, what do I need to look at? The leading term, right? Yeah. So the limit in the numerator is simply equivalent to the limit at infinity on the function 2x cubed. Same thing in the bottom, limit at infinity for x cubed. Is everybody okay with that? Before you actually evaluate this limit and say that it's infinity over infinity, you need to simplify the function first. So 2x cubed divided by x cubed. All we're doing is computing the limit at infinity on the function 2. Which of course that limit would be 2. Let's simplify. So what does that mean? The function f of x, what happens on the function of f of x? What does that tell us? A what?
A horizontal asymptote.
Right. A horizontal asymptote at y equals to 2. Again, we know that because the limit at infinity tells us the end behavior. On the positive end, the function is looking like 2. The vertical line 2. Or sorry, the horizontal line 2. So I ran out of room. You could compute the limit at negative infinity. You'd see it works out the same exact way. You're still going to end up with 2x cubed over x cubed. It's still going to simplify to 2. And as x approaches negative infinity on the function 2, the limit is still 2. Yeah.
So just to clarify, for like finding end behavior, we have to calculate the limits for both the positive and negative infinity?
Correct.
Okay.
Yeah. In general, and this is where like knowledge of functions is super helpful. Like in general, when it says end behavior, yeah, it is always both limits. It's always both ends, positive infinity and negative infinity. Specifically here, if you recognize, hey, that's a rational function, so whether I compute it at positive or negative infinity, those functions always have at most one horizontal asymptote, then it's sufficient enough to compute the limit at infinity or the limit at negative infinity, but not both. Again, that's only for rational functions. So if that's confusing as to when we can do one but not the other, then just always do both to determine end behavior. So we'll go ahead and write this out too. The function f of x has a horizontal asymptote at y equals to 2. I'll just use the same color because we're talking about the same 2. And so, does anyone have any questions on that? You're not in practice. You're probably not going to evaluate it like that, right? You're gonna say that the limit on that original function at infinity is just the same as the limit of the leading term in the numerator divided by the leading term in the denominator. So like that's probably your first step, and then your second step, as x approaches infinity, simplify that algebraically. But I just wanted to break this up into the pieces that we've looked at and that we've kind of justified so far. But sort of in practice, that's kind of how it works out. So don't feel obligated to write all of these steps. It's mainly you're going to go from start to here and simplify. All right, from an algebraic point of view, when we look at this rational function f of x, how do we determine the horizontal asymptote on that function? We said, well, what's the degree of the numerator? It's 3. What's the degree of the denominator? It's 3 as well. When the degree of the numerator and the degree of the denominator were equal, they said you have a horizontal asymptote at the leading coefficient of the numerator divided by the leading coefficient of the denominator, right? Do y'all sort of vaguely remember that? Maybe, maybe not. So leading terms are equal. I just look at the degree, or the coefficient rather. 2 divided by 1 is 2. That's our horizontal asymptote. Okay. Any questions on that? Yeah.
As far as finding the beginning and end behavior for the, see which way it goes, it would be both positive here and be like a parabola shape?
For this function?
Yeah.
Well, so like what we said is for this, I ran out of room on that thing. So what we said, let me just do this so people that listen to this video can actually. So on that function, what we said was as we approach positive infinity, that function flattens off to 2, right? So like way out here, that function is really close to this line. Somewhere, it's above or below, it's not both, right? And we sort of mentioned, we didn't actually compute, but as we approach negative infinity, the function also approaches 2 as well. So like as far as like what's happening in this region near, we would say maybe near 0, definitely not out at infinity, then you've got to look at other stuff, like where are the intercepts? What's the behavior near certain places, that kind of thing. Is that what you were asking?
But the ends are still going to be shaped like that.
The ends will still be flat at 2.
Flat.
Flat, because as x approaches infinity, the y values are approaching 2, right?
I'm saying on our 4 options we had, right?
Yeah, but this is not a, this isn't a polynomial though.
Oh, okay.
It's like a totally different type of function. It's made up of a polynomial divided by a polynomial, but it totally changes its behavior. Once you start dividing polynomials, you don't get the tapering off towards infinity. In some instances you do. Maybe you can remember certain types of rational functions that didn't have horizontal asymptotes. So we'll just go ahead and graph this too. The graph is going to be really specific. We'll see either the function above or below on both ends, but we have it as both above and below because we didn't do any other work to determine where it's at. Minus x minus 1. Okay, so that's what that function looks like, right? And we've determined that there's a horizontal asymptote at y equals to 2. So again, what that means visually is if we zoom out on this function, what's going to happen? What is the function going to look like? A what?
Flat, right?
It's going to look like a vertical line, right? Because we know what happens way out on this end and way out on this end. It looks like the function y equals to 2, which is our horizontal asymptote. So does everybody see that? There's our horizontal asymptote that we calculated. But if we zoom out, the thing's going to look flat in that area, right? So we can sort of see vague hints of red. Maybe you can't from the board because it's kind of crummy. But our function looks like the line as we get further and further out, which is exactly what our work showed us. As we get further out this way or further out this way, the function looks like y equals to 2. So yeah, make sure you're well aware of that. What we're doing here, we're computing limits on rational functions, which is a polynomial divided by another polynomial. Okay. Any other questions on this? Yeah.
So if we were to like find the vertical asymptote on this, for example, would you also be able to like simplify it down to this simplest form and then find it on that, or does that not work?
Yeah, it doesn't work. So like vertical asymptote stuff, I'm not sure where this function has a vertical asymptote. We would have to factor the numerator and denominator to determine that. But the vertical asymptote doesn't work the same way because the vertical asymptote, x is approaching what kind of thing?
A very small thing.
It's a finite number, right? So that's kind of the important thing is we're able to look at leading term over leading term only because the terms are getting larger and larger. If this were anything else, if this were even x approaches 5 million, you wouldn't be able to do this. So in the sense of a vertical asymptote, let's say, I don't know, x approaching 2, right? Like all of those terms of that function matter when x is 2 because they all contribute to the value. It's only when x is super large, like the 5x and the negative 12, don't really matter. Is everyone clear on that? Like if I'm computing a limit at any finite number on any function, I will never ignore any of the terms in that function. If I'm computing the limit at infinity on functions, that's when I can ignore things. So that's like the only exception. Any other questions or comments? I mean, it's good that we're talking about it because there are these subtle differences that sometimes need clarifying. So if you have any other questions or comments, please feel free to ask or interrupt. All right, we'll look at this one and take a break. So the limit at infinity on this function, and again, we've got a linear over a quadratic, a polynomial over a polynomial. So really the shorthand way to look at this limit is to say, well, it's a polynomial over a polynomial. So to compute the limit at infinity, all I need to do is look at the leading term in the numerator divided by the leading term in the denominator. Again, that's only because x is approaching infinity. Simplify that function algebraically before you take the limit. And that's sort of always a key element here is to simplify the function before you compute the limit, because otherwise you're going to get infinity over infinity. And we look at later in the semester how to address that kind of thing. But for now, infinity over infinity is going to be confusing because it's not 1. It's not anything that we can determine. So we've got 3x over x squared, which gives us 3 over x. The limit as x approaches infinity on 3 over x would be what? 0. The numerator is fixed, denominator is getting larger and larger, so the quotient gets smaller and smaller. That's property 3 on that from that previous theorem. Okay, so again, what do we know about 3x plus 2 over x squared minus 1? That function has a horizontal asymptote at y equals to 0. Yeah. Horizontal asymptote at y equals to 0. So now you don't have to remember all of the algebra stuff. Okay, if the degree of the numerator is bigger, what did I do? If the degrees are the same, what did I do? I don't remember any of that. I don't have to remember any of that. All I have to do is compute a limit at infinity. It tells me where my horizontal asymptote is, right? So the algebra approach was the degree of the denominator is larger,
than the degree of the numerator, so you'll always have a horizontal asymptote at y equals to 0. That was the algebra or the pre-calc approach to that. But now we see exactly why, because these lesser terms don't matter. If the degree of the denominator is always larger, then you're always going to have at least one more factor of x in the bottom than you do in the top, which will always simplify to just some number over x. As x goes to infinity, those things will always go to 0. So hopefully that sort of like ties into what you know. If you don't remember any of this stuff, what I'm saying probably is totally meaningless to you. So just forget what I'm saying and compute the limit. That's the main idea. Okay. Do y'all have any questions on that? All right, it's about halfway. We'll take a break though.
Is a vertical asymptote at 1?
Is a vertical asymptote at 1 on this function?
No.
Well, how do we know it's not at 1? Or how do we know it is at 1?
Factor the denominator.
The numerator doesn't factor, right? It's just 3x plus 2. But we know the denominator factors as difference of squares. None of these factors in the bottom go away, right? So where are our vertical asymptotes?
1 becomes negative.
At 1 and negative 1. So then from there, we could say, all right, well now what we're doing with this rational function now is building a picture of this rational function. I know it has vertical asymptotes, wherever, here and here. I guess that's straight. I don't know. So I know the function does this. I also know that as I approach positive infinity, the function approaches 0. So way out here, I know my function is super close to 0. Whether it's above or below, I'm not sure. And I know that, again, on rational functions and only rational functions, the limits at infinity are the same. So I also know that out here, the function also approaches 0. Which one it is, we don't know yet. So the way we approach this is just to say, where is the function when x is like, I don't know, negative 2? When I'm to the left of that asymptote, is it above 0 or below 0? So just plug 2 into this function, get the y value. Where is it at over here? I don't know, I'm going to plug in a number like 4 or 2 or 7 to see what the y value is. Is the y value above 0, and the function's up here? Below, and the function's down here. But now that we know also that we have vertical asymptotes here, remember you had to look at one-sided limits. Because we know as we approach the vertical asymptote, the function's doing this, or this, or this, or this. Which one of those 4 is it doing? I don't know, I have to approach negative 1 from the right, negative 1 from the left, positive 1 from the left, and positive 1 from the right to determine that. So kind of where we're at with these limits is just, it's sort of a vague sense of what the graph actually looks like. But at least on these sort of these extremities, we have a general idea as to what that is. All right, yeah, so 2 vertical asymptotes for that function, which means you would need to compute 4 different limits to determine what that function's doing at each asymptote. Does that make sense? I hope so. There's probably going to be a question on the exam like that. It says, where are the vertical asymptotes, and what's the behavior of the function near its asymptotes? So once you identify the vertical asymptotes here, to determine the behavior near the asymptotes, you have to compute those 4 limits. Okay, so if that's not clear, then just ask, but we are going to keep building on this stuff.
It's like we forget 2.4 is not over just because we're done with it, right? Do y'all have any other questions on this? So we'll take. All right. So what we'll look at now, that's really the more, reducing this by sort of looking at it through the lens of a polynomial over a polynomial. Definitely the most efficient way to view those. The harder way or the longer way is to divide all terms in both the numerator and the denominator by the highest power of x in the denominator. So, I guess functions of the form f of x over g of x when there's powers of x involved would make more sense. But for example, this one we just computed, the longer approach is to look at the limit at infinity, and since the highest power of x in the denominator is x squared, we're going to divide all of these terms by x squared. So we're dividing everything by x squared. So we've divided everything by the highest power of x in the denominator. Now we've just reduced what we can reduce or simplify what we can simplify. And we have the limit as x goes to infinity. We've got 3x over x squared. That's going to be 3 over x. Can't do anything with the 2 over x squared, so we leave that alone. X squared over x squared and 1 over x squared. Just another way to see, technically what we're doing as well. So then, as x goes to infinity, what does 3 over x approach? 0. Do you all agree? As x goes to infinity, 3 divided by x goes to 0. Plus 2 over x squared. 2 over x squared approaches what? Also 0. Over 1 minus the limit on 1 over x squared is 0 again. So you have 0 over 1, which is 0. Same result we had previous. So I don't know in practice that you really do it that way, but that's kind of what you're doing. So at least wanted to show one of those. Maybe for other functions, we'll look at a weirder type function in a minute where it might make more sense to look at it through this specific approach. But as long as you have like powers of x, the approach that we took prior to this is still valid. This last example is just so we can get all three of those sort of algebra situations in place. So you'll notice here that the degree of the numerator is larger than the degree of the denominator. So maybe you remember what happened in that situation, maybe you don't. But again, it's a limit at infinity on a rational function, so we're just going to look at the limit at infinity for the leading terms. So leading term in the numerator, just make sure that we're identifying it correctly. It is in order, so it's 3x to the fourth over 3x cubed. And again, before you compute the limit at infinity, make sure you simplify this. So that's just the limit at infinity on the function x, which is going to give us infinity. So what would we say here?
There is no asymptote.
Right, there is no horizontal asymptote. Because as x gets larger and larger, and on the right-hand side, if you will, the function just keeps getting larger and larger. It doesn't flatten out. So that function has no horizontal asymptotes. You get the same result if you approach, as x approaches infinity, or as negative infinity rather. Same conclusion. Does anyone have any questions? So again, as we graph this, if we graph this particular function and zoomed out, it's not going to get flat like our previous function did because it doesn't have a horizontal asymptote. We'll just look at it. Okay, so that's the function we just looked at. As we zoom out, it doesn't get flat. There is no horizontal asymptote. So there was a situation where we had the degree of the numerator was 1 more than the degree of the denominator. Do y'all remember that one? What happens there? What kind of asymptote do you get? A slant or oblique asymptote, right? Remember, slant or oblique asymptotes were linear. And that's what we're seeing here. As we get further and further out, that function is behaving like a linear function. So there's our slant asymptote right there. So how did you find slant asymptotes? Division, yeah, you had to divide those things. When I divide an x to the 4th thing by an x cubed thing, my quotient's going to be an x to the 1st thing. And that x to the 1st thing is my linear function, which is my oblique asymptote. All right. Anybody have any questions? So something a little bit simpler to look at is this one here. As x approaches infinity, we have the same kind of procedure. That's just 2x squared over x, which is 2x. So again, we have a function that doesn't have a horizontal asymptote, but we can look at it a little bit differently just to kind of see how that plays out. So I'm going to take my 2x squared plus 6x minus 2. I'm going to actually divide it by x plus 1. Because it's kind of like an improper fraction. With these things, if the degree on top is larger or the same as the degree on bottom, then it's improper. So we're going to make it proper by dividing through. Yeah. So if you remember long division, it's sort of based off of this leading term here that we're dividing. And we say, all right, well, here's x. How many times, or what do I need to multiply that by to get 2x squared? And then we put that up here. So I need to multiply that by a 2x. And then from here, we take that and multiply it there and there. So we have our 2x squared plus 2x times 1. And then what did we do?
Subtract.
Yeah, you have to subtract it, just like numerical division. You have to subtract that number. Here we have to subtract off that polynomial. So we subtract off all of this. 2x squared minus 2x squared is 0, 6x minus 2x is 4x. Then with numerical division, you bring the next number down or digit. Here we're just going to bring the next term down and then repeat that process. What do I need to multiply by x by to get 4x? Positive 4. Distribute the 4 to the x plus 1. And then subtract off that result. I mean, really what we're after here is the remainder. We already have our linear quotient. So I guess just to finish it, we'll go ahead and determine the remainder. I guess we're writing it in blue. So we've got a -2 minus 4, which is -6. So all of this work means the function that we started with, 2x squared plus 6x minus 2 over x plus 1 is equal to what? Two x plus 4. Yeah, what happened with the remainder? Remember, we're still trying to express a quotient. So is it just the remainder? Right, good. It's the remainder over your divisor. This is also this long division is also a valid and useful strategy if you're going on to Calc 2 when you start doing integration. So we have an equivalent representation of the original function. So instead of computing the limit on the original representation, we'll compute the limit on the alternative representation because they're the same thing. We'll say now compute the limit as x approaches infinity on this function. And so like ignore that 2x plus 4 right now. As x goes to infinity, what happens to the -6 over x plus 1? Numerator is -6, denominator gets larger and larger. That whole thing approaches 0. So I know we didn't really, technically compute the limit, but what we're seeing here is that's equivalent on this piece anyways. We didn't compute that limit yet, but we definitely know as x approaches infinity, this piece goes to 0. So as x goes to infinity, that original function that we dealt with, it doesn't change the fact that the limit still approaches infinity, right? We just have that it's equivalent to 2x plus 4 at infinity, which tells us that on that function, as we get further and further out this way or this way, that function is going to look like 2x plus 4. Yeah, 2x plus 4 still goes off to infinity, but now we have this sort of governing the behavior of the function. And so that's kind of the reasoning behind why oblique asymptotes worked as well. So we still see that this is infinity, not contradicting our original result, but this shows that the function, I'll just say the function, we're referring to that, whatever that one was, the function, whatever all that stuff, I just don't want to write all that again. This function, this shows that that function acts like 2x plus 4 for large x values.
Because that function was equivalent to this right here. And we know as at infinity, that whole thing is basically behaving like 2x plus 4, or equivalent to 2x plus 4. So let's just look at the graph for that one as well. So there's that function. Again, as we get further and further out, this is kind of like computing the limit at infinity. What does the function look like at infinity? Well, it's starting to look like this line. What is that line? It's 2x plus 4. Further and further out, you can't tell the function from the line, 2x plus 4. Does anyone have any questions on that?
All right, then we're gonna shift gears a little bit if there aren't any questions, and remind ourselves, this is sort of an aside, but necessary for certain limits. Yeah.
I was gonna ask, what would the wording look like if you asked us a question like the previous one? What, if you asked us and you wanted us to find the 2x plus 4, what would the question ask, really? If you're not trying to find the limit, but that value.
So it could be something like, what is the end behavior of this function? In that sense, we would just compute the limit at infinity and say that it's infinity, right?
Yeah.
It could say, what's the end behavior of this function? If an oblique asymptote exists, determine that.
Got it.
But as far as determining the oblique asymptote, that's an algebraic thing. It's not a calculus thing. We're just looking at it through the lens of, as x gets larger, sort of the governing behavior. Okay. So what is the square root of x squared equal to? X. Okay, so most people would say x, but it's not. So we're going to talk about this. If the square root of x squared did in fact equal x, let's just check. The square root of 2 squared is the square root of 4, which is 2, right? So here the square root of 2 squared is 2. Well, what happens when that number is negative? What's the square root of negative 2 squared? Well, it's the square root of 4, which is also 2. So if this were true, then we would have something different here, right? If this were true, this would say that this has to equal negative 2, right? The square root of something squared has to be the same thing as you plugged in. Of course, we know that's not equal to negative 2. So the square root of x squared is not x.
Absolute value of x?
It's the absolute value of x. We know when we take the square root of a number, it's always positive. The square root of x squared is the absolute value of x. So it absolutely depends on where x is when you simplify stuff. If you remember, the absolute value just means it's a piecewise function. So
if we then check it this way and we say, all right, well, the only difference here is we're putting that there, right? And so we see that each case comes out to be 2. So we'll see, like, the reason we're talking about this is because, we're gonna come back to a couple more things here, but the reason we're talking about this is because we see functions like this sometimes. It's not a rational function. The thing in the numerator is a polynomial, but the thing in the denominator isn't, because you've got that square root involved. So we sort of have to take a detour to solidify this idea before we start looking at limits at infinity on those mixed type of functions, if you will. Okay, so in continuing with this notion, what would the square root of x to the 4th be? What's the square root of x to the 4th? X squared. Everybody agree? What's the square root of x to the 6th? X to the 3rd? What do y'all think? So let's back up. Why don't we need absolute value here? Why isn't the square root of x to the 4th the absolute value of x squared? Right, because if you square a negative, it's still positive. I mean, we could say this, it's just sort of redundant to say that, because it's the same thing as just x squared. So the square root of x to the 6th, we get x cubed, but is x cubed always positive? No, it depends on where x is, right? So the square root of x to the 6th should be what? Absolute value of x cubed. What's the square root of x to the 8th? X to the 4th? Is x to the 4th always positive? Regardless of where x is, x to the 4th is always positive. One more, what's the square root of x to the 10th? Yeah, we need the absolute value again. Absolute value of x to the 5th. It's the same definition. We've just replaced x in our absolute value definition with x cubed. So the absolute value of x cubed just means that if you have a positive number here, if you have a positive or 0 input, it's just the function itself. If the input is negative, though, we just need to take the negative of it. Okay, so the reason this matters is because when we look at end behavior on certain types of functions, remember it's the end behavior at positive infinity and at negative infinity. Depending on what end you're at, sometimes you're just plugging in large positive numbers, but other times you're plugging in large negative numbers. And we see that in instances like this, and with the square root of x, that it totally matters what your numbers are. Instances like x to the 4th and x to the 8th, it doesn't really matter what your numbers are, because whether they're positive or negative, x to the 4th, x squared, it's always positive. Okay, so with that in mind, we'll look at this example. State the end behavior of this function. Again, it's not a rational function, so we need to look at both ends. Remember, rational functions are the only functions that we have where it's sufficient to look at just one end and not both. Any other functions, we've got to look at both. So the limit at positive infinity and negative infinity.
So honestly, we could go through the longer approach and say, all right, well, what's the highest power of x in the denominator, and divide everything by that. I still think the approach of looking at leading term over leading term is a lot more straightforward here. So this is the way we're going to look at it. I mean, we can look at it both ways, just so you can see that it's, this is the most straightforward as we can make this. So we're going to have our 10x cubed here. The leading term in the denominator is the 25x to the 6th, but we are taking the square root of that, right? So that's going to stay like this. So leading term, we simplify after we do that, before we calculate the limit at infinity. Okay. So we've got, again, if you want to simplify stuff algebraically and then put the final simplified version in front of the limit, that's totally fine, because I know it's tedious to write limit. Okay, so we still have our 10x cubed here. What's the square root of 25x to the 6th?
5x to the third.
5x to the third? Does everybody agree? Absolute value? All right, so let's go ahead and put that just so we're totally clear. Square root of 25 is 5. Square root of x to the 6th is the absolute value of x cubed. Does everybody agree? Now, whenever you're working with an absolute value, no matter what you're doing, any math class, whether you're taking the derivative or the integral or whatever, you always work with an absolute value without the absolute value. So once we've established that, all right, well, we've got an absolute value involved, we have to then establish, can we get rid of the absolute value? And if so, how does the absolute value have to go away? So to answer that question, we just have to look at, where is x? Is x positive or is x negative?
In this case, it's positive.
It's positive, right? How do we know that? Well, x is approaching positive infinity. X is a super large positive number in this limit, right? X is a large positive number. So what does that mean is the absolute value of x cubed is? It's just positive, it's just x cubed, right? Remember, the absolute value is the thing itself if the input's positive. All right, so that's 10x cubed still. We know the bottom now for large positive numbers that the absolute value of x cubed is just x cubed. So we've got this thing we're working with now, and we can simplify that algebraically. What is that limit? It's 2. So we know on the very far right that this function has a horizontal asymptote at 2. So what do you think changes when we approach negative infinity? Something changes. What changes though? Yeah, well, let's just look at it then. Okay, that's one end. Here's the other end. So is it okay that we just take it back to where we did leading term over leading term? Just to save us up. And again, we'll simplify this the same way. That's the limit as x approaches negative infinity.
we've got 5. Again, absolute value of x cubed. On the bottom, we don't want to work with the absolute value. So how do we rewrite the absolute value of x cubed here? Keeping in mind where x is.
Well, it would become positive on the bottom, but in the numerator, it would still be negative.
So yeah, technically though, the numerator is the one that's positive.
Oh, yes, that's what I meant.
Okay, right. So okay, like the absolute value of something, right? We'll just replace x with something, right? It's just that something, the same thing, if this thing is positive or 0, right? It's the negative of that thing if, sorry, I keep wanting to write x, if that thing is negative. That's all the absolute value ever does to anything, regardless of what's in it. So for our x values are large negative numbers, what happens to the absolute value of x cubed? Right, and that's what you were saying. I was just trying to get everyone else on board. But it just turns into negative of that thing. It's just negative x cubed. Because if that thing is, if x cubed outputs something negative, how do you make it positive? You just multiply by -1. So this turns into, we're going to just write it out. This is the limit as x approaches negative infinity on 10x cubed over 5 times negative x cubed. Large negative numbers also, just write this here. Absolute value of x cubed for large negative numbers is negative x cubed. So what's that limit? -2, right? We have the x cubed cancels out. We have 10 over -5, which is -2. So this function actually has 2 horizontal asymptotes. You've seen at least one function that does have 2 horizontal asymptotes. Does anybody remember prior to this class? What? I thought I heard somebody say it. Okay, so tangent and cotangent have vertical asymptotes. So which ones have the horizontal? The inverse, right? Because remember when inverse is the x's become y's, the verticals become horizontals when we invert. So inverse tangent, inverse cotangent are 2 functions you've seen before that have 2 horizontal asymptotes. So it is entirely possible, as evidenced by this example. And we'll graph this just so we're certain. Okay, so there's that weird function right there. We have 2 vertical asymptotes. Or sorry, horizontal asymptotes, not that much. All right, so as we approach positive infinity, notice our function approaches +2. And as we approach negative infinity, the function approaches -2. I guess it's not going to cooperate. All right, for just for reference there. Does anyone have any questions on this? Okay, so don't go through it and just look at leading term and say, all right, well, this one's going to be positive 5 and the other one's going to be negative. The other asymptote's going to be at negative 5. It really depends on the function that you're dealing with. It also depends on whether or not you have terms that are outside of the radical. So if we had terms outside of the radical, then it would change things. And you do have one like this where terms are outside of the radical on your homework. So this way works in some instances, but I think overall that it's better to think of it limits at infinity for function divided by another function as, okay, what's the highest power of x in the denominator? Then I'm going to divide every term by that power. So just to see how that plays out, we're not going to change the result of what we just computed. But if we do, let's just look at the limit at infinity on this function. We would say, okay, well, since I guess we've got to figure out what's the highest power in the denominator on x. X to the 6th. So does that mean we divide everything by x to the 6th? No, why not? Because it's under the radical, right? The top doesn't have a radical. So it's what we're going to do, and maybe we don't compute that. Maybe we just simplify this in that sense first. So what we're going to do is we're going to say, yeah, everything in the bottom under the radical gets divided through by x to the 6th. But things outside of the radical need to be divided by what? So I think everyone agrees with this, right? Everything in the bottom gets divided through by x to the 6th. It's the highest power of x in the denominator. But again, it's under the radical, so what we're dealing with is, on the bottom, we're really dividing every term by this. Without the radical, what is this?
Absolute.
Right, it's the absolute value of x cubed. So that's what we're dividing by. Notice we don't have a limit yet, but as soon as we tack on a limit, then we know exactly what to do with that absolute value, depending on where x is. So I'll just leave the top as is, because it does, at this point, it does matter what limit we're computing, as we saw from our calculations above. I'm just going to leave this alone on top. And then we can simplify the thing under the radical. It's just 25 plus 1 over x squared plus 2 over x to the 6th. Okay. So that's how that thing's simplified. We're not doing anything illegal algebraically. It's still the same function, right? We basically said, okay, multiply the numerator by the square root of x to the 6th and multiply the denominator by, 1 over the square root of x to the 6th. So we've multiplied top and bottom, or divided top and bottom by the same thing. So algebraically, these two things are equivalent. Is everyone okay with that? No, this is sort of a long-winded way to look at this, but it's helpful to view this is what we're doing as well as what we did above. So then when I would come to compute the end behavior, let's say the limit as x approaches infinity, well, x again, large positive number, I don't need the absolute value, so this function just becomes 10x cubed over positive x cubed, minus 3x squared over positive x cubed, plus 8 over x cubed. All over the square root of 25 plus all that stuff. And this, again, is kind of a longer way to write all of this stuff out too, right? Just kind of piece it all together. Is everyone okay with that? X is positive, absolute value just turns into the function itself. Yeah.
Are you going to test us about the easier part of it?
I don't have a preference on how you do it. Like I said, you got to be careful though, because if the function was like, like what if we had 10x cubed minus 3x squared, and it was like the square root of 25x to the 6th, whatever, plus x squared, and then out here we had plus another, 3x cubed. Right? As long as you know one or the other, I think you would be fine. But again, if we're just going to take this simpler approach, the leading term in the numerator here is still 10x cubed. But what's the leading term in the denominator? It's not as straightforward, right? Because this is 25x cubed, really, without the radical. And this is 3x cubed. So we wouldn't just say, okay, the leading term in the bottom is 27x cubed. I mean, I guess we could, but it's really at that point, does that make sense to you to do that? So if it does, then great, but otherwise you can think of it this way and it'll still give you the same result. So whichever one works for you in the sense that you understand it and in the sense that it gives you correct results, I would use that one for sure. I mean, it may seem like a stupid thing to state, it's totally obvious, but I'm not going to test you over one or the other. It's either or. But yeah, totally valid question. Just, if we can show it different ways, then a lot of times I'll do that because it might make sense to some or it doesn't make sense to others. Again, the only thing that's going to be different with this limit, and of course we'll simplify all that, but the only thing that's going to be different with the limit at negative infinity is that we're going to divide the top by a negative x cubed. Because now we're at negative values. And so we see that just totally flips the value from positive to negative. Is everybody all right with that? Any questions? All right, so simplify. You're going to get this limit to come out to be -2. Simplify this to +2. So you see in the denominator, right, that you end up with just 25 because as x goes to positive or negative infinity, 1 over x squared and 2 over x to the 6th, both of those are going to 0. So in either case, you just end up with the square root of 25 on the bottom. What changes is the top, depending on where x is located.
or in general, what changes are the things outside of the radical when x is positive or negative. Okay. So any questions on that problem? A couple more things in this in here. We're going to look at the end behavior of our exponential function e to the x and logarithm. So what is the end behavior of e to the x? First of all, when we think about the ends, the functions that we've looked at, for the most part, the ends, the domain of those functions have been, we have been able to go out to positive and negative infinity, right? What's the domain of exponential functions? This is what?
They're positive.
Right.
0 to infinity.
Domain of exponential functions would be from negative infinity to infinity. That means, as far as the ends are concerned on an exponential function, they are out at infinity. So what we're asking here is two things. What is the limit as x approaches infinity on e to the x? And what is the limit at negative infinity? So even if you remember the graph, you immediately have the answer. If you don't remember the graph, then what is, as x goes to infinity, remember e is like 2.71828. What is that number raised to a larger and larger number? What happens there? It gets bigger and bigger, right? Okay, so we know, I forgot the graph, but I definitely know this now. Out here, this function is way up here at positive infinity. How about as x approaches negative infinity, what happens e to a large negative number?
0.
It approaches 0. Does everybody agree? Think about it this way. It's e to the negative infinity. We treat that like any other negative exponent is 1 over e to the positive infinity. 1 over a super large number is a super small number. So we know here out at this end, the function is really close to 0. We know it's positive because exponentials are always positive, unless they have a negative in front, right? So, oh yeah, that looks familiar. I think the graph of e to the x does something like this, right? Okay, so that's the end behavior for e to the x. Again, you can get that just by remembering the graph as well. And so, in practice, sometimes we can look at, combination of like exponential functions and ask the limit at infinity on 7e to the x minus 15 over 3e to the x. What would that be? Zero? What do y'all think? So in order for that to be 0, the top has to be fixed at some number, and the bottom has to be getting larger and larger. I think we can all agree that the bottom does get larger and larger, but what happens to the top? It also gets larger and larger. So aren't these two things really comparable? Does the minus 15 on top matter at infinity? No, because 7e to the infinity is much, 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 much larger. So we can look at it how we've looked at all of the others. What's the lead? Instead of like thinking of leading terms, you can think of what's the dominant term in the numerator and in the denominator. So of course that just simplifies to 7 over 3 as x goes to infinity. The function goes to 7 over 3. Does that make sense?
Still kind of that leading term over leading term kind of thing. And like the certain things we haven't addressed, like what about an exponential function like 5 to the x over 2 to the x? What do you think about that limit? Does not exist. How come?
Both get into infinity.
Okay, good, right. So the limit is infinity because the top gets larger much more rapidly than the bottom, right? So even though they're both going off to infinity, this function on the top grows a lot more rapidly than the function on the bottom. So something like this we'll be able to show later in this class that this limit is infinity. What if we flipped the results, or the functions rather? What if it were 2 to the x over 5 to the x? What would that be?
Since the bottom's getting more, it's more
Yeah.
rapidly getting to zero, wait, to infinity. There you go.
Yeah, so the bottom here is the bottom function is growing much more rapidly or larger than the top function. So something like this, the limit would be 0. I'm not gonna test you over these exponentials, only e to the x, but I think it's important to know, like, in the sense of growth rates, or what's the bottom function doing compared to the top function, can sort of help build a little bit of intuition. Is what you're looking for. Okay. All right, so that's the exponential, e to the x. You can also, look at this in the same way. If we ask what's the limit as x approaches infinity on e to the negative x, and what's the end behavior? In other words, what's the end behavior of e to the negative x instead of e to the positive x? What happens there?
Well, you get the reverse of what the other one was.
Yeah, you get the reverse of what we have up here, right? Because e to a negative large number is 1 over e to a really large number. I don't know, if you want to think of it this way, think of it this way. It's helpful. And this is e to the negative of the negative infinity, which is e to the infinity, which is infinity. As far as the graph goes, remember the negative up here just flips it across the y-axis. So here's the graph of e to the negative x. So however you remember those things, we can compute them directly, more or less. Okay. Anybody have any questions on e to the x? So then, what's the end behavior for the natural log? So first of all, we're talking about the end of the function. What's the domain of the function? Not all real numbers. Remember the natural log in relation to e to the power of x, or what are those two things in relation to each other? Inverses, right? When you look at an inverse, the domain of an inverse becomes what on the becomes the range, right? Because you just switch x and y. So the domain of e to the x, all real numbers, becomes the range of the natural logarithmic function. The range of e to the x becomes the domain of the natural log function. So what is the range of this function here? Yeah, it's 0 to infinity. The range of this function is the domain of its inverse. So when we talk about the end behavior of the natural logarithm, yeah, it makes sense that we can approach infinity, but we can't approach negative infinity. It doesn't make sense. So end behavior 1, limit at infinity on the natural log. What's the other end behavior? The limit as x approaches what? 0. Yeah, more specifically though, can we approach 0 from both sides?
No, from the right.
No, so this has to be the limit as x approaches 0 from the right. Oops, ln of x. So there's our end behaviors for the natural log of x. So we have to compute those limits. If you remember the graph, then these should be pretty easy too. This is infinity. We said the range was infinite, right? So eventually we end up plugging all x values, and the function outputs all y values. But what about the limit at as you approach 0 from the right? What do the y values get closer to? What do the function values get closer to? Negative infinity, right? Remember, natural log of x looks like this. E to the x had a horizontal asymptote at y equals to 0. So when we invert that, the horizontal asymptote becomes a vertical asymptote at x equals to 0. So as we approach 0 from the right, this function just keeps dying off. Okay. So that's it for today. Let me know if y'all have any questions on the homework. I'll be around this weekend checking emails and stuff. So have a good weekend.